3 minutes ago, the silence of the cosmos was broken. From the black sea of the night sky, an object no one had ever seen before appeared, faint, moving, and strangely self-contained. It bore no familiar tail, no glittering plume of vaporized ice, only a quiet glow drifting between the Earth and two other wanderers of the deep, the interstellar comet known as 3 Atlas, and another named K1 Atlas. This new arrival was given a temporary name, S2025V1 Borisov, and with it came an echo of recognition. The name Borisov has weight among astronomers. It evokes the same quiet persistence that once revealed the first confirmed interstellar comet to humanity. Now 6 years later, another of his discoveries had entered the scene, and again the world of astronomy was holding its breath. It began in the early hours between the 2nd and the 3rd of November, 2025, in the remote stillness of the Margo Observatory in Crimea. Beneath the sharp, cold sky, astronomer Gennady Borisov leaned into his telescope. He was searching through the endless digital frames, images that reveal the faintest smudges of movement against the backdrop of stars fixed in their ancient geometry. And there it was, a dim, unlisted glow, shifting gently from frame to frame. At first glance, it was almost nothing, a ghostly blot on the edge of perception, but it moved. And movement, in the vast stillness of the cosmos, means life of another kind. For a moment, he must have paused, that delicate hesitation of a trained observer recognizing the boundary between the known and the unknown. The coordinates didn't match any catalogued asteroid. Its trajectory slid slightly away from the well-worn lanes of the main belt. In hours, Borisov sent his data to the Central Bureau for Astronomical Telegrams, the clearinghouse of discoveries. Along with his report came precise coordinates, time stamps, and a measured brightness of 12.1 stellar magnitudes, faint yet undeniably real. The comb of the object measured nearly half a minute of arc across, with no visible tail. A diffuse, spherical glow and silence. The preliminary code assigned to it indicated something unusual, something that didn't fit the ordinary mathematical patterns of solar system debris. News travels fast in the astronomy community. Before dawn's first light touched the observatory domes of Europe, the alert had spread. Russia, Japan, Ukraine, and the Canary Islands all turned their instruments to the sky. Each night's data flickered across international forums, a chorus of images and numbers, and all confirmed what Borisov had seen, a compact bright coma with no tail. Only 2 of 10 early reports mentioned a faint suggestion of extension, a thread of light too unstable to be sure it was real. Some thought it a processing artifact, a trick of background stars. Others wondered if the laws of cometary behavior were being quietly rewritten before their eyes. By the morning of November 3rd, the discovery had made its way through global verification lists. The Central Bureau issued an official alert. The object now had a formal designation, C2025V1 Borisov. The name itself carried a charge, an almost poetic symmetry. The discoverer's surname echoing the one attached to the first interstellar visitor ever found by human eyes. A call went out for rapid response observations. Amateur astronomers, observatories, universities, all were urged to gather data, measure light curves, and record spectra. The world's telescopes pivoted, their lenses now aimed toward a quiet patch of sky where an enigma was unfolding. Images arrived from Palomar, from Sukagawa, from Lviv, and from La Palma. They showed the same uncanny thing, a growing sphere of light without a tail. From October 29th to November 3rd, its brightness increased by more than 5 magnitudes, an almost 100-fold surge in visible intensity. For a celestial body of this type, such a rise was extraordinary. Normally, comets reveal themselves through jets of gas and long tails, stretching millions of kilometers. But S2025V1 Borisov seemed to defy that script, glowing brighter while keeping its form intact, almost as if hiding its core beneath a veil of luminous dust. For skywatchers, this was more than a new dot on a chart. It was a cosmic whisper, suggesting that something unprecedented might be unfolding near our world. Was it a collision? A rare alignment? A new kind of body entirely? Theories multiplied as the days passed, each one hinting at new possibilities that stretched from the familiar to the fantastical. Every night, observatories exchanged their findings: brightness curves, motion vectors, even whispered speculations about material composition. The excitement was tangible, though wrapped in the calm professionalism of scientific inquiry. The object's path placed it between the Earth and Comet 3 Atlas, a known interstellar traveler whose behavior had already defied predictions. To some, this alignment seemed more than coincidence. Two luminous bodies, both unexpectedly bright, both almost tailless, drifting in neighboring sectors of the sky. Could it be mere geometry? Or was there a hidden connection, perhaps a shared origin or a synchronized event echoing from the depths beyond our solar system? In the pre-dawn skies of early November, the constellation of Virgo framed this silent drama. From both hemispheres, amateur astronomers began to report their own sightings. The object was now within reach of mid-sized backyard telescopes, its coma a gentle round glow suspended among the stars. Even the faintest image seemed to carry a quiet, unnerving beauty. It was as if the universe had paused for a moment to reveal something fragile, unclassifiable, and fleeting. And so, the story of S2025V1 Borisov began, with a smudge of light, a watchful eye, and the humbling reminder that the cosmos still keeps its greatest secrets hidden behind the faintest flickers in the dark. What exactly had Borisov seen? Why did this object shine so strongly yet refuse to grow a tail? And what connection, if any, did it share with the strange behavior of the two comets named Atlas, each moving through its own impossible geometry? As telescopes turned, data streamed, and scientists searched for order within the unexplainable, one truth grew clear. The silence that followed the discovery was not emptiness. It was anticipation. The universe once again, waiting for us to listen. The nights that followed the discovery of S2025V1 Borisov became a living tapestry of observation and wonder, woven from data points and starlight. In every time zone, telescopes swiveled toward Virgo, where this quiet intruder glowed with impossible steadiness. What had begun as a faint, uncertain blur in Crimea was now the focus of a global astronomical campaign, a rare moment of unity where amateurs and professionals shared the same breath of curiosity. The international community, guided by the coordination of the Minor Planet Center and the Central Bureau for Astronomical Telegrams, confirmed that this was not a routine object. It was real, it was active, and it was behaving in ways that no cometary model could easily explain. As reports accumulated, a clearer image began to emerge. The coma of Borisov's new object remained almost perfectly symmetrical, a soft sphere of luminescence rather than the elongated plume typical of comets nearing the Sun. Its brightness rose swiftly, from 17th magnitude to 10th within only 5 days, an acceleration rarely seen outside of outburst events. Yet, there was no visible fragmentation, no jets, no tail structure. The body brightened as though illuminated from within, and then stabilized, defying the physics of sublimation and dust dispersion that govern traditional cometary activity. Scientists at the European Space Agency's Planetary Science Division noted that this could indicate the presence of unusually large dust grains or non-volatile materials dominating the coma, a composition perhaps more asteroid-like than icy. But the orbit told another story. Using a cascade of positional data from Palomar Observatory in California, Siding Spring in Australia, and the Subaru telescope in Hawaii, astronomers computed the trajectory with increasing precision. The orbital elements suggested a highly eccentric yet still bound path around the Sun, placing the object in a temporary state between a long-period comet and a possible interstellar intruder. The preliminary eccentricity hovered just below 1, too close to the escape threshold to dismiss the possibility of an interstellar origin. This was enough to ignite a familiar sense of awe. Was this another messenger from beyond the solar system, like Borisov's own discovery in 2019, the interstellar comet 2I Borisov, or was it something even stranger? An object born within our system, but shaped by forces we still did not understand. Teams from the Institute for Astronomy in Kyoto and the Max Planck Institute for Solar System Research began simultaneous photometric campaigns, measuring how the object's brightness changed with phase angle and solar distance. Their results only deepened the enigma. The light curve refused to conform to the canonical models of sublimation. Instead of a gradual increase followed by a slow decline, S2025V1 exhibited quasi-stable brightness levels with subtle oscillations, as though it were rotating and exposing surfaces of varying albedo. But there was no periodic modulation sharp enough to confirm a rotation period. The object's nucleus remained hidden within a dense fog of dust that scattered light evenly in all directions, masking any shadow or flare that might reveal its shape. Meanwhile, spectroscopic measurements from observatories in the Canary Islands and Ukraine began to arrive. These spectra were expected to reveal the fingerprints of common cometary gases: cyanogen, diatomic carbon, hydroxyl, water vapor. Yet their signatures were faint, nearly drowned by the continuum of reflected sunlight. The absence of strong emission bands indicated either an unusually low gas content or a composition dominated by refractory materials. Researchers proposed that S2025V1 might be a fragment of an ancient devolatilized comet, a remnant of a body that had long ago exhausted its surface ices and now wandered as a dormant core that had somehow flared back to life. Others suggested an impact-triggered release, perhaps caused by thermal stress or micro-collisions with meteoroid dust. But another observation complicated the picture. On the 4th of November, photometric data from La Palma indicated a slight color shift in the coma, from neutral white to a warmer yellow hue. The change was subtle, yet measurable. Such color evolution could signify that sunlight was scattering off larger particles, possibly silicate dust rather than icy grains. This was reinforced by radar echoes obtained by the Goldstone Deep Space Communications Complex, which detected an unusually strong, broad reflection pattern consistent with a dense cloud of micron to millimeter-sized dust. The radar albedo was higher than typical for comets, again pointing toward heavier, rockier material. The question loomed larger. What kind of object could bridge the line between comet, asteroid, and something else entirely? Amid the swirl of hypotheses, orbital modeling offered both reassurance and mystery. S2025V1's trajectory placed it between Earth and the interstellar comet 3 Atlas during the early days of November. Though their orbits never intersected in three-dimensional space, the apparent alignment was striking. To ground observers, the two appeared to trace twin arcs across the pre-dawn sky, as if drawn by an unseen hand. Simulations from NASA's Jet Propulsion Laboratory revealed that this alignment would persist for several days, a fleeting geometric illusion born of perspective, but one so precise that it created the appearance of a cosmic choreography. The two luminous bodies, nearly tailless yet brilliant, moving together through Virgo's celestial fields, invited both poetic speculation and scientific scrutiny. The coincidence extended beyond mere appearance. Both Borisov's object and 3 Atlas exhibited similar anomalies: unexpectedly high brightness, stable comae, and a stubborn lack of tails despite their proximity to the Sun. Solar physicists at the Lockheed Martin Solar and Astrophysics Laboratory began to wonder if recent solar activity could be involved. The Sun had erupted in a series of strong coronal mass ejections during late October, sending waves of charged particles through the inner solar system. Could this influx have affected dust dynamics or surface cohesion in these comets, suppressing the formation of tails while amplifying their core luminescence? The hypothesis gained traction when, despite continued solar storms in early November, neither object displayed any sudden morphological changes. The sunlight struck them, yet their bright coma held steady, as though shielded or indifferent to the solar wind. The scientific intrigue soon drew the attention of space agencies beyond Earth. On November 5th, researchers at the Chinese National Space Administration confirmed that the Tianwen orbiter, currently stationed around Mars, had captured low-resolution imagery of S2025V1 from its unique vantage point. The short sequence showed the same concentrated sphere of brightness, lacking a visible tail. Although the data offered little in terms of detail, it provided valuable cross-solar geometry, confirming that the optical properties of the coma remained consistent across vast observation angles. Meanwhile, NASA's Mars Reconnaissance Orbiter was tasked with attempting its own imaging sequence, though by that time the geometry was less favorable. The European Space Agency considered redirecting one of its solar orbiters for spectroscopic capture, but mission constraints made it unlikely. At the same time, terrestrial observatories raced to extract every possible clue. High-resolution imaging from the Very Large Telescope in Chile hinted at a structured inner coma. Faint concentric ripples, possibly jets or shells, expanding outward from an unseen core. The dynamics of these features suggested slow rotation, maybe one complete spin every 24 hours. Still, no trace of a tail appeared, even in long exposures. The absence was deafening in its implication. Whatever forces normally drive material outward were either suppressed or acting in a fundamentally different way. Dust dynamicists turned their attention to radiation pressure theory. They modeled the V parameter, the ratio of solar radiation pressure to gravitational pull on dust grains. For grains larger than a few microns, V falls below 1, meaning sunlight cannot easily push them away. In S2025V1, the dominance of large, heavy grains could explain why the coma remained compact, glowing but unstretched. Such a dust population would scatter light efficiently, creating an intense, isotropic brightness but no extended tail. The same reasoning fit the observations of 3 Atlas as well, suggesting that both objects might belong to a peculiar class of comets whose dust emission is dominated by heavy, refractory material rather than fine, volatile ice. But if so, where did this material come from? One idea proposed by a joint research group from the Ukrainian Academy of Sciences and Kyoto University suggested that both Borisov and Atlas might have originated from a similar region of the outer solar system. Perhaps a dense fragment cloud left behind by an ancient collision billions of years ago. These fragments could carry a unique mineral composition, a blend of carbon-rich silicates and metallic inclusions that resists sublimation under sunlight. Over time, such objects could wander inward, glowing fiercely under the sun, yet refusing to sprout the traditional cometary tail. By November 7th, 3 comets shared the same pre-dawn stage: S2025V1 Borisov, 3 Atlas, and K1 Atlas. Each traced its own arc across the celestial sphere, their apparent proximity producing the illusion of convergence. But while their paths seemed to cross from Earth's viewpoint, their true distances spanned tens of millions of kilometers. K1 Atlas, perched in the constellation Leo, shimmered with a golden hue. Faint, but distinct. It was the only one among the trio to display even a vestigial tail, a narrow filament discernible in long exposures. The other 2 remained resolutely tailless, as if bound by an unspoken cosmic symmetry. In the midst of this visual spectacle, the community found itself divided between cautious empiricism and reverent wonder. Was this a coincidence? 3 comets, 1 sky, and an illusion of alignment. Or was it a rare manifestation of deeper orbital resonances, perhaps a gravitational echo left by ancient perturbations from Jupiter, or even passing interstellar bodies? Computational models at the Paris Observatory simulated possible origins, tracing orbital integrations backward thousands of years, yet none revealed a definitive link. The orbits diverged too early, too chaotically. The shared visual alignment, beautiful as it was, appeared to be nothing more than a cosmic accident. Still, accidents in astronomy often lead to discovery. The intense global observation campaign produced one of the most comprehensive, real-time datasets ever gathered on a new comet. Thousands of amateur astronomers uploaded images to centralized repositories, allowing photometric tracking at intervals as short as 10 minutes. Machine learning models at the Harvard-Smithsonian Center for Astrophysics began analyzing this collective stream, identifying micro-variations in brightness that might hint at sublimation pulses or internal fragmentation. Early results showed tiny oscillations, minute, rhythmic changes in luminosity occurring every 3 hours. Some suggested these could correspond to vents opening and closing as the nucleus slowly rotated, releasing jets that were too weak to form tails but strong enough to maintain the coma's glow. The behavior of S2025V1, paradoxical yet consistent, became a catalyst for rethinking the physics of cometary dust. Papers began circulating, preprints uploaded at an accelerating pace. Terms like quasi-refractory coma and tail-suppressed emission regime entered discussion threads. In the background, space weather continued its restless pulse. Solar flares, magnetic storms, auroras stretching across polar skies, all providing new parameters for study. Yet through it all, Borisov's discovery remained calm, a stable lantern in the changing heavens. By the second week of November, the story had moved beyond confirmation. The object was no longer just a discovery. It was a mystery, redefining boundaries. Astronomers spoke of it as a silent teacher, compelling the scientific community to confront how much remains unknown about the subtle interplay of dust, light, and gravity. Each observation, each measurement, was another page in an unfolding chronicle of the solar system's uncharted complexity. The question that now dominated discussions was no longer whether S2025V1 was interstellar or local. It was why it glowed at all, and what secret within its dark nucleus allowed it to shine so purely without a trace of the expected. The answer, for now, remained suspended in that fragile space between knowledge and wonder. The place where science touches the edge of imagination, and the universe whispers its next riddle to those who dare to look. Every celestial discovery carries within it a story, not just of stars and dust, but of human endurance, patience, and quiet wonder. The tale of S2025V1 Borisov is no exception. It began, as such stories often do, with a single person standing beneath the sky, trusting the dim whisper of photons caught by glass and metal. Gennady Borisov is not a scientist who works within the marble corridors of a national observatory. He is a craftsman, a builder of his own instruments, a man whose faith in precision was forged in solitude. Years ago, he assembled his first telescope from hand-polished mirrors and spare components, guided only by his meticulous sense of geometry and his stubborn belief that the cosmos always rewards those who pay attention. It was this same persistence that, in the year 2019, led him to find the first verified interstellar comet, 2I Borisov, an event that altered the way humanity viewed the boundaries of its own solar system. When history chose to repeat his name 6 years later, it did so with quiet symmetry. The new object that now bears his signature is more than another entry in astronomical catalogues. It is a continuation of a lifelong dialogue between a man and the sky. Borisov's second major discovery came not from chance, but from a ritual of discipline, scanning, calibrating, reviewing frames late into the night, listening to the faint hum of the observatory around him. He has spoken often, in his few interviews, about how discovery feels less like an act of finding and more like an act of listening. The universe, he says, is never silent. It only speaks in a language of patience. That patience has now brought humanity to the edge of a new cosmic mystery. S2025V1, still gliding between Earth and the distant path of 3 Atlas, remains under scrutiny from every major observatory. Its orbit has now been refined to a precision of fractions of a second of arc. Its motion mapped so accurately that predictions extend decades into the future. By mid-December, it is expected to reach its perihelion, passing within roughly 0.55 astronomical units of the Sun, close enough for solar heating to test its resistance. If the current models are correct, it may brighten further without ever developing a tail, a silent lamp orbiting in defiance of textbook expectations. To those who observe it, this behavior has become almost personal. Amateur astronomers, working from backyards, rooftops, and mountain ridges, share images night after night, composing a living atlas of change. They record the color of the coma, its minute fluctuations in intensity, the subtle breathing of light around a hidden core. Each image, each line of data, becomes part of a collective human effort to understand something that exists hundreds of millions of kilometers away, yet feels intimate, because it responds to our gaze. The collaboration between professionals and amateurs has never been more seamless. Data uploaded in the darkness of one hemisphere is analyzed by dawn in another. What once took weeks now unfolds in hours. The discovery has evolved beyond a single person's moment of insight into a shared act of exploration, binding people across continents through a mutual reverence for the unknown. Borisov himself continues to work quietly, declining the sudden attention that has gathered around his name. Those who know him describe him as a man of few words, more comfortable among telescopes than reporters. His notes from the night of discovery reveal a calm precision. The coordinates, the magnitudes, the timestamps, all written without flourish. Yet within those lines lies a pulse of emotion that needs no translation. Every astronomer knows the feeling, the instant when the infinite becomes tangible, when a new point of light on the screen is no longer just a pixel but a message, arriving across immeasurable space and time. The telescopes that now study S2025V1 belong to an era of unparalleled sensitivity. The James Webb Space Telescope, though still in contention for observation time, has been proposed as one of the few instruments capable of resolving the structure of its coma in the infrared spectrum. If scheduled, its data could reveal the chemical composition hidden beneath the visible glow. The carbonates, silicates, or complex organics that might tell us whether this body is truly native to our solar system or a wandering fragment from another star. The European Southern Observatory's Very Large Telescope continues nightly observations measuring the polarization of light reflected from the dust. Early analyses suggest an unusual alignment pattern, possibly indicating magnetic influences or electrostatic cohesion among large dust grains. Such properties could reshape our understanding of how small bodies evolve under solar radiation. In laboratories on Earth, scientists are now recreating miniature versions of the comet's environment, exposing silicate mixtures and carbon-rich powders to simulated solar light and plasma. They are searching for the missing mechanism, the one that could produce the brilliance of a coma without releasing the cascading tail. Experiments suggest that surface sintering, the process by which dust grains fuse under thermal cycling, might create a compact glowing sheath around the nucleus. If confirmed, it could mean that S2025V1 and 3 Atlas belong to a new evolutionary class. Transitional comets, halfway between active and dormant states, their brilliance born not from sublimation, but from light scattering on tightly packed dust shells. In this hypothesis lies a poetic symmetry. The brightness of these bodies, Their refusal to display tails could symbolize a state of transformation, celestial remnants on the verge of fading, yet radiant in their last act. They are reminders that even in apparent stillness there is movement. Even in decline there is beauty. As the nights of November give way to the colder clarity of December, the three comets, Borisov, 3 Atlas, and K1 Atlas, continue their slow divergence across the sky. The brief illusion of alignment dissolves, revealing the vast distances that separate them. And yet, for a short time, they shared the same canvas of dawn, their lights mingling in ways only our planet's vantage could allow. For the observers who rose before sunrise to catch their fleeting glow, this alignment will remain a memory of wonder. Three travelers painted upon one horizon, bound by perspective if not by physics. The story of S2025V1 will not end soon. Its orbit will carry it out of easy reach within months, fading beyond the capabilities of small telescopes. But the data gathered will endure. Countless images, spectra, and positional measurements archived in digital repositories that future astronomers will study with instruments not yet invented. They will look back on this object as we now look upon ancient star catalogs, searching for meaning in the faint signatures left by those who watched the heavens before them. Perhaps they will confirm its interstellar origin, or perhaps they will uncover evidence that it was born from the same primordial dust as our own world. Either way, it will remain a bridge between questions, an unanswered equation in the language of creation. For Gennady Borisov, the man who gave this new wanderer its name, the reward lies not in fame, but in the continuation of a conversation that began the moment humanity first looked upward. His work stands as a quiet declaration that the universe is still unfolding, that discovery is not the domain of machines alone, but of human vision, of eyes that search for patterns, of hands that build instruments from nothing, of minds that refuse to accept that we have seen it all. In the wider sense, the discovery of S2025V1 reminds us of our place within the cosmic order. It tells us that even now, in an age when satellites map every corner of our planet, there remain frontiers untouched, mysteries unsolved, and lights uncounted. The night sky is still alive, still capable of surprise. Each new object, each anomaly, is an invitation to humility. It asks us to look again, to listen longer, to remember that the laws we write are only approximations of a reality more complex and wondrous than we can yet imagine. And so the story concludes as it began, with silence, but not the silence of absence. It is the silence before revelation, the quiet heartbeat of the universe waiting for us to notice. Somewhere, far beyond the blue of daylight, S2025V1 Borisov continues its drift through the void, a glowing ember in the cold sea of space. Its light, though faint, reaches us across that distance, a reminder that discovery does not always come in brilliance, but sometimes